Hi, my name is Vishwanath Alasila. I am an associate professor at Rama Institute of Technology, and I am offering this course together with Professor Ramakrishna Pasumurthy of IIT Madras. We are going to now move to module 11, the first lecture of this. We are going to be looking at some applications of some of the theory which you have learnt in the previous lectures, and the specific application which we are going to focus on is on navigation. To be more specific, we are going to be looking at the notions of how transfer functions, filter design, so what are done in Bode plots and those kind of things, low pass and the high pass filter. So, we are going to be looking at how they are relevant in the context of navigation. Okay. We could take a lot of different applications. There is a specific reason why I have taken navigation, and it is as follows. So, in most control courses, we see that the traditional application areas are for electric circuits like power systems or mechanical systems which are robotics and so on. But navigation is another very big application area, and there is quite a lot of interesting control systems, also modeling, which is very relevant and required in navigation. It is important for all students to remember that when you talk of control systems, controls does not exist independent of a model, right. So, which is why any controls course, the first 1 or 2 units will be predominantly about the model of the system, only then we go for analyzing say how to design controllers and so on. In fact, the first 3 units will always be about modeling and analysis of systems. So, we will look today at how we can model the problem of navigation, and we will see how to bring in 2 specific concepts of control system, which is the filter design and of course modeling. Another reason why navigation is very important is many young engineers, when they go to industry or higher research, so when you are looking at autonomous vehicles, or you are looking at say the flight control of an airplane or a missile, the story of navigation becomes very important. And some of you would have already heard of these filters called the Kalman filters. Maybe if you are lucky, you would have even heard of particle filters and so on. So, these filters are very standard and they are very important in the field of navigation. Specifically, the Kalman filter is a classical feedback control design written in a slightly probabilistic or stochastic manner. So, while Kalman filter is one of the standard techniques we use for navigation, what I will be presenting in these series of lectures along with some experimental demonstrations is a complementary filter. And the complementary filter is a very simple filter. It is a combination of low pass and a high pass filter, and we take the signals coming out of these 2 filters and we fuse them in order to get a more meaningful answer to our navigation problem, right. What the Kalman filter does is something far more complex, and it turns out for a lot of applications we do not really need the Kalman filter, which is a feedback control design. It is enough to do just you can think of this as pre-filtering. We can just filter our signals and still get very meaningful answers to our navigation problem. So, this is a combination of modeling and control. So, let us go ahead. And if you look at the slide over here, you will see that I have used this word stories. And the reason for this is it is always nice to know how certain fields have evolved, right. So, be it control systems, be it signal processing or whatever, and navigation is actually a very fascinating topic. So, the story of navigation is as old as the story of mankind or even animals and all species. And we will see with a few stories how navigation has been accomplished over the past say thousands of years, and we will see that the basic concepts of navigation have remained very similar over the last 5,000 years. What has changed, of course, is a technology. For example, GPS was not there more than a few decades back. right. So, technologies have changed, but we will see that the story of navigation, the basic concepts have remained very similar. Okay. So, first let us start with some stories, and the content is, so first we will see what is navigation, we will see various types of navigation. So, we will look at some things, some nice stories from history which include some sad stories as well, how animals navigate. Then we will look at one specific aspect of navigation in a little bit of detail called dead reckoning. Okay. We all have actually studied dead reckoning slightly before in the concept of trigonometry. We will see that. We will conclude this lecture with studying reference frames. So, the basic idea of a reference frame is when I describe the motion of an object, it is with respect to my own reference frame. So, if I see, for example, this duster moving from this point to this point, this motion is with respect to my reference frame. So, the really bad way of explaining this is, for me this is a motion from right to left, whereas for you this would be a motion from left to right. Okay? That is a very simplistic way of explaining, but if you remember that we all live in a 3D world. So, we describe every point in space with a x, y, z say coordinate system, and my coordinate system will not be the same as your coordinate system, right. And it is very important when we do navigation to be very clear about which reference frames we are going to use. So, we will conclude with the notion of reference frames. Okay. So, what is navigation? Well, there is many definitions and all definitions are equally true. The basic idea is that it is a technique or the art of moving from one geographical area to another, right. So, you could move from Chennai to Bangalore, you could move from place X to place Y and so on. Now, when you want to navigate or move from place X to place Y, the first and most important notion in navigation is to know one's own position, right. Say you want to move from this point to this point, right, through whichever route you want to take, whichever trajectory you want to take, you have to know where you are, otherwise it is literally impossible to know where you are actually going to land up, right. So, we will see some examples of calculating our own position, and using our known position we will see how we calculate the path to a certain object. Okay. Then we will look at very briefly, maybe in just one slide or so, other navigation sensors, very advanced navigation sensors, some of which are based on GPS, some of which are based on Wi-Fi localization and camera based localization. So, localization basically means knowing where I am, locating my position. So, we will do this very briefly just to give you an indication of how advanced the field of navigation has become. Our primary focus will be on inertial sensors. Okay. We will see that a little bit later. So, point number 5 is really crucial, and it basically says, while the nature of sensing GPS sensors, cameras, Wi-Fi's and so on, while they have changed, even computing has changed over thousands of years, 3 basic concepts of navigation have always remained and is still being used in exactly the same way. The first is know where your current position is. Okay, we already talked about that. The second is using information about your current position and velocity. We will see that velocity is not the only requirement, but for now let us assume velocity. So, using the information about your current position and velocity, you can actually compute what will be your future position. And finally, you always will make use of external landmarks to make sure that you actually do not get into what I call hopelessly lost. This is actually a technical problem called drift. Okay. Before we go ahead, let me give a small indication of how we normally navigate. If I need to go, if I need to move from this position where I am sitting right now to, if I need to leave this particular room, I have a fair estimate of the map of this area, right. So, I know where the walls are, I know where the chairs are, I have a rough estimate of the distance which it takes for me to go from this point to exiting the door. If I close my eyes and I start walking, and all of you should really try this experiment at home, If I close my eyes and start walking, we have a reasonable idea, as long as you do not fall down, we have a reasonable idea of how much distance we are covering, right. So, for example, if I close my eyes and walk from this point to the end of the room, I will not say that I have walked 1 kilometer, I will not say I walked 1 meter, I will be in the range of maybe 5 meters, 10 meters or something. So, I have a fair idea of how much distance I have covered, in which direction I have gone, alright. So, that is a little bit the problem of navigation. If I open my eyes, now I can see external landmarks, I can see there are chairs over here, I can see there is gaps in the corridor, all these additional so called landmarks, they help me to navigate far better, okay. So, in navigation we always, at least the advanced navigation, we always use two kinds of techniques. So, the first one would be called, it is actually called dead reckoning, and it basically is a means to estimate my future position based on my current information. And the second thing is the use of external landmarks. And for those of you who read this subject in a little bit more advanced way, you will see that GPS is actually one of these beautiful concepts where we use external landmarks, which are satellites in space, to actually help us to localize where we are. And these inertial sensors are the ones which are going to be used to estimate my future positions and so on, okay. So, the concluding point of this slide is the last line in red, that the technology for navigation has changed dramatically, but the overall concepts are still very similar, alright. So, what are the various types of navigation? Obviously, we had say coastal navigation, you could also include land based navigation, right, in the ancient days. So, people would move from say from Calicut all the way to Indonesia. So, that is entirely the coastal navigation, the sea routes. Then people may have wanted to move from let us say 2 different kingdoms in ancient India, and that will be the land based navigation. We will be focusing more on a little bit on coastal navigation in our lecture. So, coastal navigation basically is navigating alongside a coast. Alongside a coast means you usually are able to visually observe or see the coast, and we will see why that is very important. And the second type of navigation is dead reckoning, we will go into a lot of detail about that. The third type of navigation is celestial navigation, where we use stars, planets, moon, so on, to actually help us to navigate, and we will again go into a little bit of example to see this. We will look at the concept of dead reckoning with electronic navigation in a lot of detail, by specifically using what are called inertial sensors. And inertial sensors, many of you are aware of at least one of them, the famous accelerometer, which you get in your phone when you rotate the phone from portrait mode to landscape mode, right, the screen also rotates. And we are also going to look at another sensor called the gyroscope, okay. So, first we look at coastal navigation, we look a little bit at dead reckoning, how humans do it, how animals do it, and then we look at celestial navigation, and finally the rest of the whole lecture series will be on electronic navigation for dead reckoning. Okay, so what is coastal navigation? It basically, loosely speaking, if you talk of ancient times, coastal navigation was when you need to move from one point on the coast to another point, maybe hundreds of kilometers away, you would use specific natural features, okay. So, for example, you would use maybe some mountains which are along the coast, okay. You would use certain species of animal, fishes and other kind of marine species which you see along the coast. You would actually use tides and currents. So, along the coast there would be certain regions which have very strong currents and other regions which have really very mild currents, right. So, you would use all this information to be able to say that I am at this particular position, At a different position, my tides would be different, the species of animals would be different, I may not have a mountain at all, and so on. Or you could use lighthouses, light vessels, and all these other features. So, if you look at this particular map over here, it is called a nautical fishing chart, and all the pink shaded areas, maybe it looks like magenta, all the pink shaded areas are where fish is available in plenty. So, a person who is actually navigating along this coast, okay, say in this particular route, okay, if the person actually is able to see that there are lots of specific types of fish in this particular area, and okay, they will actually have a fair approximation of their location. They will know that they are somewhere within this vicinity. Whereas, if they come in this region and they see a different species of fish over here, they will know that they could be somewhere in this vicinity. They will certainly not be here, right, because those species of fish do not exist over here. So, these are the nautical fishing charts. Like that, you of course have the nautical charts for the coastline, which depict the mountains, so on and so forth. Okay. So, that is coastal navigation, and this was one of the predominant ways that ancients would actually navigate along the Indian coast or other countries as well. Let us see one very interesting story of coastal navigation from history, and this focuses on the Emperor Alexander's great march to India, where he fought some battles and then eventually had to go back, and we will see what actually happened. So, there is this place called Takshila over here, and Alexander, after he finished his battles, he wanted to march say further into India, but his generals they were actually very tired. There was almost going to be a rebellion among the soldiers. So, they convinced Alexander that okay, let us go home, enough, war is done. So, a decision was taken that from Takshila they would actually have to go back to Babylon, where the empire was. So, let us say Takshila was somewhere over here, and Babylon, which is modern day Baghdad in Iraq, was somewhere over here. Okay. And the idea was that Alexander and his army would actually navigate from Takshila to Babylon or modern day Baghdad. And based on the surveys which his people had done, they believed. So, if you look at this yellow line over here, this is it is the Indus River. So, it is much more clearly visible as these blue lines in this particular chart, right. So, this is the Indus River, and what they believed is if they sailed down the Indus River and they reached this coast, okay. So, this particular coast, they wrongly believed that this coast was the same as the upper reaches of the Nile, which is where would I say, yes, which is over here, which is much closer to Baghdad and much easier to get than from Takshila. And the reason why they believed that this area over here was basically the upper reaches of the Nile River near Egypt was because the local flora and fauna, the species of animals and other things, fishes, actually matched that of these two places. So, the kind of fishes you would get here were very similar to the fishes you would get there. The kind of trees which would grow were very similar in both cases. So, what Alexander did then, they marched all the way down to this coast, and what do you get? You do not get the Mediterranean Sea over here, right. You get the Arabian Sea when you come over here. Having discovered the mistake, now because this was a completely wrong coastal navigation, they now had to march all the way across the desert with thousands and lakhs, maybe lakhs of soldiers died before they reached Baghdad. So, this was a great story in coastal navigation, which almost ensured that Alexander's army was wiped out, and actually he never recovered from that, and he eventually died. So, the story here is that coastal navigation, okay, which is built on using certain features like say flora, the mountains along the coast and so on and so forth can be highly erroneous. And we will see that this is a typical feature of most navigation techniques, alright. So, that is about coastal navigation. Now, let us move to dead reckoning. Dead reckoning is a very simple concept and very easy to understand. So, of course, coastal navigation is not always possible. You may not be at the coast, or you may not have interesting landmarks to observe even on land, and then navigation becomes a little bit tricky. That is where you use the concept of dead reckoning, which is the technique of computing your current position based on your past known position and the speed and direction in which you have gone. And the problem in 2D, let us look at the problem in 2D, it scales to 3D in a very similar way. The problem in 2D basically says the following: if you start at this particular location, okay, and you moved 45 degrees, 45 degrees with respect to something, but let us say in this case it is with respect to the x axis. If you start at this position and move 45 degrees with respect to the x axis, and you moved at a speed of say 1 meter per second, alright, in this direction, where would you be after 10 seconds? Where would you be after 10 seconds? Now, this is very easy to calculate from trigonometry, right. So, if you call this initial position as x old and y old, we know from trigonometry what these two coordinates will be, right. I encourage you to try this before you move on to the next slide. And it basically follows from the basic trigonometric relations of this one, where d is basically the distance which is travelled. Okay. So, this is basically dead reckoning in 2D. Note that we are not talking about accelerations, velocities and other kind of things measured by sensors. We actually know at what speed we are travelling at, like how the ancients would do, have an estimate of the velocity you are travelling at, and based on that you actually calculate your current position. Although this is done in 2D, exactly the same concept extends to 3D as well. Okay, so that is dead reckoning. Now, just a small example of how we would do dead reckoning in the ocean. So, this is in marine navigation, these charts which is shown over here is basically one way of computing or plotting. So, we would actually say plotting your course or plotting your path, right. So, they normally use the word course in navigation. And the basic story here, it goes as follows: your ship has started at 9 AM in the morning and it is moving at a speed of 10 knots. Knots is a marine way of computing speed. So, it has a certain relation to meters per second or kilometers per hour. So, your ship is moving at 10 knots at an angle of 90 degrees, at a heading of 90 degrees, and this is a magnetic heading. So, with respect to your compass which looks at magnetic north, you are moving at an angle of 90 degrees with respect to magnetic north. Then what the navigator does is to plot what would be the expected position of the ship, alright, at 10 AM. And in this particular example, what has happened is at 10 AM the ship captain decided to maintain the same speed and to move at the same course of 90 degrees with respect to navigation. And then the navigator waited till 10:30 when the captain decided to make a change in the path or the course of the ship to 60 degrees, moving at the same speed. Then what the navigator does is to plot what is the expected position at 11 o'clock. Okay, so, apart from the first one, all these are expected positions, okay, where you expect your ship to be. So, in the same way they would plot all the positions. Now, we will see in the next lecture that if this is the computed position based entirely on dead reckoning, the actual position, now I am drawing this roughly, this would not be the real case, it may be far worse than what I am drawing. The actual position may actually be something like this, and this would be the actual position where the ship actually lands up. And the reason for this massive difference in the estimated position versus the actual position is because of the condition called drift, which we will go through in a while. Okay, so that is how you do marine navigation. Dead reckoning, you are not using any coastal landmarks or any such thing, just only dead reckoning. How do animals do it, or even humans? So, if you look at this particular desert ant, it is Saharan desert ant, and it uses a technique called proprioception. It is a biological term, where it basically means that I have an idea of how much I am actually moving. It uses a technique of proprioception, and it is able to count its leg movements to estimate the distance travelled. So, it is able to count the leg movements, right, to know how much distance it has travelled. Notice that we still are not talking about how this guy gets the course or the direction of movement. I'll come to that in the next slide. Okay. So, animals, humans, all species, they actually have a means of estimating how much they have actually travelled. That is the basic notion here, and it is based on dead reckoning. So, let us look at celestial navigation, and we will see how these ants are actually able to navigate accurately with celestial navigation. So, celestial navigation is the art of navigation by using celestial bodies, stars, moon, and it is really how it was done in the ancient days. The cool thing about celestial navigation is that while it is not very accurate, okay, you can always be sure, reasonably be sure about your position, and we will see why that is so. So, you will never be completely off. So, you will never have errors the way that you had in your dead reckoning, which leads you to really a completely erroneous position than where you really are. Celestial navigation avoids that problem. In fact, we will see one example of this shortly. Okay, and the example is something like this. So, let us say you are in a ship in the middle of an ocean, and this is your current position. You do not know what your current position is, by the way. So, I am telling you, you are over here, but you are the ship captain and you do not know where you are. All you can see, assume it is night time, all you can see are the stars in the sky. So, you are somewhere in the middle of an ocean, all you can see are the stars in the sky. The question is, where exactly on earth are you? So, how would you solve this problem? So, the way it was done was actually this. So, let us say you are at this unknown position in the middle of the ocean or somewhere, and you see a star over here. I do not know how to draw a star, I am imagining it something like this. So, you see a star over there, right. So, this is all your beautiful ocean over here, it is a moonlit night, maybe you are listening to some nice Lata Mangeshkar songs, but you have absolutely no idea where you are. Now, how would you actually compute your position? So, to be more precise, let us say you have seen this star at 10 p.m. at night. Now, you have a book, I believe it is called the star map, and the location on earth based on where the stars are. It basically says, if you are able to see this particular star at 10 o'clock, then if the star is perfectly above your head, okay. So, if I draw a perpendicular line from the star and it falls on earth over here, okay. If the star is perfectly above your head at 10 p.m, you know this location, more specifically you know the coordinates of the location. It is usually given in latitude, longitude, altitude, but we will skip that for now. So, you know the actual location where you are if the star were perfectly above your head. The star is not above your head, you are somewhere over here, right, and you are seeing the star from this position. Now, let us say that you have a means of measuring the angle at which you are able to observe the star from here, let us say it is some 55 degrees. Okay. I am standing here, I am seeing the star is 55 degrees with respect to me. I have this fancy book which says that at 10 o'clock, if I were here, I would see the star exactly above my head. Now, it turns out with very simple trigonometry, you can actually compute what is the distance from your unknown position to the actual position if the star were exactly above your head. Okay, this is very simple trigonometry, and it basically assumes that you know the distance from your position to the star, and the ancients had really interesting methods of calculating this, again based on standard trigonometry. So, if you know this distance, alright, and you can calculate this, you would assume that you are somewhere over here. However, life is not that simple, because what would actually happen is, all it is saying is that with respect to x, y, z, which I have drawn over here, I can be anywhere, okay, at a particular angle of 55 degrees, right. It can be here, it can also be here, 55 degrees and so on. I can be anywhere on a circle, right, and you do not know exactly where you are. So, actually it is a complete circle, I cannot draw it here because it looks weird, but otherwise it is a complete circle, and anywhere on this circle you will see this particular star at 55 degrees. So, you know approximately where you are on a circle, but you still need to know where exactly you are, and the way they would do that is to use another star. So, you would see another star, and see I can now draw stars properly. You would use another star, and you would again do exactly the same. So, you are in this unknown position, I have a certain angle reference to the position, and it says that maybe I am at some, I do not know, 110 degrees or something like that, right. I really do not know exactly, but say some 110 degrees, and let us say you have seen this other star again at 10 p.m. at the same time as you have seen this star. We again know from this from the star map chart of ours that if the star were visible at 10 p.m. you would have to be somewhere over here at this new x prime, y prime, z prime. So, I now know two specific positions if the star were above my head, x, y, z, other is x prime, y prime, z prime. We saw with x, y, z, I am able to calculate this distance, and I know that I am somewhere on this great arc, on the great circle. With this new position I can again do the same, and what I would get is a different arc, right. So, maybe it is something like this, which means that anywhere on this circle I will see this star at that 110 degrees, whatever we mentioned, right, anywhere in this, on this circle. Now, we see that these two circles are intersecting at this position, right, and that is your actual position. For those of you who are a little bit more curious, you may have either guessed by now, or you may want to know that you still cannot get an exact position fix by doing this, because this area over here is really large. With two circles, you take the intersection of those two circles, you will actually get a very large area, and you could be anywhere in this area and get exactly the same information. So, the even better way to do it is now to look at more stars in the sky, 3 stars, 4 stars, 5 stars, then you get all these circles, and the intersection of these circles will become a much smaller region, right, and that much smaller region will actually be where you really are. So, this is how you would do celestial navigation. It is basically the problem of triangulation, nothing more than that. And triangulation we see is a technique that's being followed even these days. So, right, so that's, we have done dead reckoning, we have just done celestial navigation. Now, let us see what happens when you combine dead reckoning with celestial navigation. Note that celestial navigation, it is not always easy to get an exact say distance measurement, because as we have seen in the previous slide, we get a fairly reasonably accurate position of where we are, but that position is not accurate to within a few meters or something like that. Like you would say that if I am able to see the star from this position, and after doing all these calculations which we have done over here, you would say I am approximately in this area, and that area could be as large as a few meters. And why that is not good? It is not good if you are an ant or an animal which is searching for food, right, and then it needs to come back to its house. So, let us say there is this ant over here, and by the way this is also true of autonomous vehicle navigation. So, you are over here, you do all this hangama, you are looking all over the place and you find some food over here. Now, when you come back, you need to know exactly where you need to come back. If your position calculation is erroneous even by a few meters, the ant instead of going to this nest may land up over here, where I do not know, there may be some predator which eats ants, I am not sure. So, it is not really a very advisable thing to use only celestial navigation. We know that dead reckoning is very inaccurate. When you combine dead reckoning with celestial navigation, we actually get a far more accurate picture, and the idea is very simple. Dead reckoning is accurate for small time scales. Specifically, this means if I am navigating for a very short amount of time, like say a minute or two, dead reckoning is very accurate. Celestial navigation is celestial navigation has bounded errors for any time scale. So, even if I navigate for 1 hour, 10 hours, 100 hours, 200 hours, 1 year, I know that my error will always be bounded. We have seen that in the previous slide. If I am able to see the correct stars or any such thing, I will always know reasonably well where I am. It will not be perfect, but it will be reasonably well. So, when you combine dead reckoning with celestial navigation, you can get the accuracy at the small time scales, and you will always make sure that you do not have unbounded error, which is a common feature of dead reckoning through drift for any time scale. And in fact, the desert ants actually use these kind of things. So, what this guy does over here, it uses these proprioceptors which counts the leg movements, it knows how much distance it has travelled, it uses the concept of optic flow to get a feel of the velocity. So, you take this object again. So, let us say that I move this object like this, right. I have an approximate feel of the velocity of this object, right. I know that it moves from here to here in about a second. The same thing if the object is static and I am moving across, like I am an ant which is actually moving across this, or I am a robotic autonomous vehicle moving across this, I have exactly the same perception of movement and I know how fast I am moving with respect to an object. So, that is the concept of optic flow. So, it gives velocity whereas the proprioceptor gives distance. So, now you have a lot of information with you. And then this desert ant, it actually uses the position of the sun for the relative angular information, right. So, this is the celestial navigation which is done. So, it combines so that it always knows approximately where it is, it never gets really badly lost, and the dead reckoning ensures it is always accurate in these small time scales. So, the fusion of these two will make sure that the ant always lands up at home, alright. So, that is a combination of dead reckoning and celestial navigation. Okay, I could not resist putting this slide because I think it is really fascinating and it shows how we ancient Indians actually did some amazing navigation. So, Indian navigation is around 3000 BC old or even older. They had a lot of trade links with Mesopotamia, which is current Iraq, and also Kuwait. It is around 2900 BC, really 5000 years ago, and the world's first dock for ships, Lothal, was built around 2400 BC. And one of the earliest navies which India had was during the Maurya time, around 300 BC. The Chola Empire, lots of us would have heard, had its influence extending all the way across these regions. And of course, you could not have done that without extraordinarily good maritime navigation. In fact, if you look at this picture over here, this is in a museum somewhere in Calicut or somewhere, I am really sorry, I am not able to recall that. They actually got the wreckage of a Chola era boat and they reconstructed based on the drawings that are available from the Chola Empire how the boats would have looked back in those days. and by those days I mean around say around 1000 AD. So, this is actually a boat which was from that era, this was beautiful. And of course, fortunately or unfortunately, as history has taught us, we had the visit from Vasco da Gama in 1498, and things changed after that, and certainly we have not done any exciting navigation, at least maritime navigation beyond that, until the last few years when the Indian Navy now has started to go to Antarctica and other really neat places. So, it is a brief history of the great adventures of Indian navigation. There are some extraordinarily good books on this, it is fascinating and beautiful, and you should actually read this to get a feel of what navigation was in those days. Okay. So, done with history, done with stories, now let us move on to some other cool stuff. So, we have seen coastal navigation, dead reckoning, we have seen celestial navigation. Now, the more modern navigation techniques are highly based on electronics, right, and one of the most classical examples which all of you would have used or are really aware of is the GPS based navigation. So, this gives you your position on earth in latitude, longitude and altitude. Okay. So, GPS works basically by how the receiver in your phone or your GPS receiver is looking at satellites in space. The other thing is inertial navigation, we will be discussing that a lot in these lectures, and inertial navigation uses accelerometers and gyroscopes. The really accurate type of navigation on earth is by a combination of INS and GPS. So, it is basically a fusion, it is called INS GPS system, inertial nav GPS based system. And here again, as we have talked about in the dead reckoning and celestial navigation, the inertial navigation system is very accurate over small time scales, and GPS has bounded error. It is not perfect, as many of you would have observed. If you are trying to navigate with GPS, you actually get lost sometimes, like a couple of streets away from where you are, from where you should be, but it is a bounded error. So, if you are in Chennai, it will not show Bangalore and vice versa, whereas if you navigate with INS for say a few hours and you are still in Chennai, it would actually show Bangalore or something else. So, these are the standard navigation sensors which are used. Recent research has focused on the use of cameras, laser based ranging sensors and radars to also do navigation. There is also Wi-Fi based navigation. You would have possibly not used Wi-Fi, but you would have used your cell tower based localization when you would have used your cell tower based localization when you are booking your Ola or Uber vehicles. So, when actually doing the booking, it shows where your current position is on the map, and that is by the cell tower based localization. Wi-Fi localization is a similar approach based on Wi-Fi signals. Okay. So, for those of you who are really interested in looking at this, you need to look at autonomous navigation, and if you give any of these keywords, say lidars or cameras, it actually shows up a lot of really interesting literature. However, the focus of our lecture is going to be only on inertial navigation.